तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So far we have seen how to back annotate our design files by using primarily two commands, that is ngdno, and this is the output option, and these are all the this is the output file, and input file being this, and which was obtained by Xilinx place and route, and then final back annotated file which is sequential circuits underscore bano dot which we gave, and was derived from the input file nga, which is the output of this first phase, and you need ngd to Verilog conversion to do affect this back annotation file, and standard delay format file was also created, and then we also saw that we need to replace some two statements by commenting out these two here as shown here. And now in the test bench we should make sure that this back annotation file is added in place of .vm file we had used earlier for the optimization, and that is I think this is the one. So if I will just increase the font size for this, so you can see this. So include sequential circuits underscore bano. I have already done this, and with this we will be running. So now next step, let us see, we will just follow this is to compile. Before we compile, we will have to open the model sim. The primary goal is to back annotate and get a file, back annotated file, and this is very much akin to the source file, your design file, and the same file, this file will have to be taken into the model sim and simulated, and make sure that after back annotation the gate delays take effect. That is the primary purpose of doing this, and in order to do this one, let us open, I mean if model sim is, I think it is already open here, and so we have to key in the command here, and that has also been done earlier. I will just show the command that we have to give is vlog is another the command version. This is the prompt, it is like a Unix prompt, and inside the model sim window, and vlog is the one which recognizes as a compiler, and what we had to compile is the library file, because after back annotation you will get all the primitive cells coming into this file. So, basically the MUX, LUTs which I had told earlier, these primitive cells will get reflected into this file, and if you open out back annotation you will precisely see this, and you have to compile that file. That is this file is actually inside a test bench. That is what we have already seen some time back, and wherein we saw that this is the one, this is the test bench actually, and in that we have added included back annotation file instead of .vm file, which we did for optimization earlier. And now in addition to this test file which contains the back annotation file, you have also to mention some library files required for recognizing the modules of the primitive cells, etc. They are all basically modules, and they will be recognized and are located in the Xilinx path where it is the primary Xilinx software is loaded, and that entire path will have to be given here, and include this library there. So, this includes all the primitive cells library. Along with that you have to compile, and of course your back annotation file. When you run this, it does the compilation, and after this we have to make sure that the 3 files mentioned in 7, that is previous step we had done here, that is here we had a .v back annotated file, then SDF file, and as well as your test bench which is edited for including back annotation file. So, these things 3 files are what is referred here, that is what is referred here, and check it by using, you can use a directory command to see, make sure that these files are present, otherwise you will get an error if one of the files is missing. And next step is we will see this step and then go to the model sim in order to do both. So, basically 2 commands that you have to execute in the model sim prompt, and next step is suppose a new directory is not created already, you may have to create a work directory there, that is what it says here, create a new work directory and load the work file using the command vsim. Vsim is the one command for the simulation, and it is actually for loading the design file, because we have compiled with the back annotated file, and that corresponding file will have to be loaded. That is what we say, whenever you have a compilation it should be followed by simulation, and that is what we do here, and naturally that is in work directory, and the name it has is precisely same as your top module, which is the test bench, which includes the back annotation file. So, we will do this together, and we can even finish the last step, and you can use as usual wave signals in order to see the waveform for further analysis, and since there is a difficulty in you viewing this on the TV monitor, we will as usual show it on paint, and note that the new waveforms reflect the actual gate delays being the result of the back annotation. So, this is what you have to bear in mind, and so now let us see the model sim window, that is here. So, those first is compilation, this has been already keyed in here, and this vlog minus y, all that what we have already seen, and sequential circuits underscore test.v. So, let us execute this, just give a return. So, it has done the compilation. During the compilation it say it reports compiling module x underscore buff, then IPAD, OPAD, invert, tri-state buffer, flip flops, OR gate, exclusive OR, MUX, and so on. So, this is as a result of including the entire Xilinx library as such here, and thereafter you had to have the test bench also compiled, and that is already done here, and prior to this it compiles the your design. Actually, this is a back annotated design, and this back annotation is not specifically mentioned because what we had declared as a module is actually sequential circuits in the design. So, we did not change the module name. So, what it reports is only the module name, as you see here. So, after it has successfully done the compiling work now. So, what the next step is to load this file. this is vsim work dot sequential circuits underscore test. This has loaded. Once again you can see that iPad, OPAD all are reported here. It is loading module by module. Each one is called work directory, and along with the extension, whether it is a test bench or the design or the library here. And one the next step is to see the waveform. So, which we can use view, then signals, and then when the signals window opens, then you use view wave, then the last option is signals in design. So, this is what you are already familiar, and it's already open here. So, now what we need to do is run this. So, it has run, and once again this is crowded here, you can't make out anything here. So, what we will do is I will directly open some of the examples. I will consider a couple of examples in order to explain the result of back annotation. So, as I mentioned earlier, the gate delays must manifest here in the waveform, and let us first open what is called as sequential counter, which we used for the after optimization. We saw a small delay, and this is what it is. I will before zooming in, I will just explain what it is. The whole scene is available in just a single page. So, you can see here a counter which being reset 0 corresponding to a reset pin here, and you note that reset happens right here, whereas only after a delay this 0 has been reset. So, earlier it was not the case. So, probably in the optimization, even in that phase, I think we did not get any delay as such. There was a delay in somewhere else. So, maybe after the when the counter started. Now, if you see here, this is the positive edge pulse here of the clock, and the actual counter advances not at that one, but only after a delay. For example, this may be around 2 nanoseconds or so. So, and every count is always delayed by the same amount. So, once again you can see here, and it is counting from 0, 1, 2, 3 and so on, right up to 9. So, we will see one more view of this towards the end of this count. So, the counter is it counts from 0 through 255 in steps of 1, and then revolves back, and it keeps on going like that in a cyclic fashion. And there are other signals which we need not really worry about, because we have already seen a couple of times earlier. So, these are all to advance the counter, then reset the counter using inputs here. I will first zoom so that you can clearly have a look. So, you can see reset clock ABC as input here, and finally a reset count. Here you can see that after back annotation, I could not find reset count as well as advance count. Advance count is totally missing. As I mentioned, it was used in other circuits. So, naturally that got dropped, because similar such signal was there under some other name. So, at the time of optimization after synthesis itself, it was missing advance count, and here also it is not to be found after back annotation. And here reset count also got changed little. So, it has renamed as some 199. So, it takes a more detailed manifestation here in as far as the signals are concerned. I mean, in the sense, if it is multi-bit where it reported as one group earlier, in this back annotation it will separate out all the signals and report separately, and it will be very tedious for you to keep track of the count, etc. So, we may not be in a position to see the actual count value in some cases. Perhaps we are lucky to see here in this case, it is a back annotated file only, as the name implies here, and opening this one, the count goes in this fashion 0, 1, 2, 3 and so on, and you can see ABC becoming 1. That is the condition we set for the counting to start, and that is precisely where it has happened. and now you can have a look at the difference. See here the positive edge of the clock occurs here, whereas the actual count takes place only here. So, this is clearly due to the gate delays associated with the circuitry for that particular path, and so is the case. You can see equal amounts it is shifted from every clock here, and clock frequency is I think same 20 megahertz, and I mean 50 megahertz, 20 nanosecond I think. So, we will open another, this is going right up to 10. So, we will continue towards the end we will see. So, that one is here, and you can see 250, 251, and ABC inputs are continuing to be 1, and the reset count is active only here at the time when it is 255. You remember that reset count is to be basically an assigned statement earlier, and that will have to get reflected the moment 255 is encountered in the counter register. But surprising thing here is it is happening in advance. I cannot offer an explanation, maybe there is a bug in the software. So, probably we may have to write to the model sim and find out why it is so, and that is not a serious thing, it is happening in advance here, both the edges you can see here, and but anyway the counting I mean after when this pulse is encountered it has to clear, and that is what is happening here. You can even see here some changes here before going to 0, it goes through some different values, but finally it settles down. So, if I zoom you may be in a position to see a little better. So, you can see 250, 251 etc. This is the counter edge here, and you can see that pulse here, and you can see this activity here, some ringing like thing. In fact, it is changing to 2-3 different values and finally only settling down at 0. That is not a handicap, because this 0 will be sensed only at the positive edge when it is stable. That is what the synchronous circuit is all about. And so, we will in addition to this we will see one more example, that is we have seen a monoshot vibrator, and here it is too crowded, we may have to go into the searching for all the signals, and anyway you will not be in a position to see, that is why we are seeing that paint zoomed version. So, we will now see there are couple of waveforms for the monoshot. This is here in a monoshot we have once again a reset, then clock, then reset for the counter. The counter is CNTD here, and as I mentioned earlier, some of the counters are totally separated out. If it is I think this is 16-bit counter, is it? If it is so, you will get all the 16 signals listed, you may have to manually group them, that will be very tedious. That is the reason why I could not show you a counter here, and so that is not a handicap, because what we are really interested is the final output itself. This delay out is the final output. You have a trigger P, trigger C, based upon 0-1 condition we set another signal called run delay, which is which simulates the start pulse of the monoshot. So, it is high here and goes low here. So, when it becomes high somewhere here, probably just before, I should have captured one more on the left, but that is not a major issue. So, what we are concerned is the only delay out, which is the required monoshot operation that we are looking for. So, the idea is we give a pulse for a start pulse for the monoshot, and the timer runs, and it starts running right at this point. If you see here, it is 75 nanosecond. This is precisely at 77 here, and you just remember it is 77 here, and it keeps on it is high here, and okay, I will zoom this. It is 77 here, this is a fourth point here. So, that means 2 nanosecond, 2 plus 75, 77 here, and towards the end, let us say this this is the delay out that we have, this is the desired output, and after the giving the trigger it goes high here, and naturally only after the second clock pulse it will start, all that we have already seen. So, we do not have to see that, and in addition to that gate delays also become operational because it is a back connected file, therefore, it is much longer it is taking, and only here it goes, in spite of the fact that clock is somewhere way off, somewhere here this is the clock, right. And we will go towards the end of this delay out, and that is there in the second towards the end. I will zoom here, it is around 5180. We started with 77 nanosecond, you remember. So, the difference is 5180 minus 77. If you take 77 as 80, 5100, and 3 extra we had take. So, it has given a time delay of 5103 nanosecond. Now, as per our program, it was setting of 255, and we also saw that clock is 20 nanosecond. So, 255 into 20 is 5100. So, if it the timer had run precisely, it would have made 5100 exactly, but unfortunately we have some 3 nanoseconds extra here. So, that is the accuracy that you can have in this design, and this inaccuracy is created not by us or by our design, there is no design flaw as such, and the basic thing is the path delay has made all the difference. So, after all delay out is dependent upon to start with, when it is switched it may have one particular delay, it may have to go through set of gates, and when it is switched off it may have to go through another set of condition. So, that means another set of gates is coming into picture. So, between these two sets whatever is the propagation delay difference will manifest as the error. So, and that is what you have here 3 nanoseconds explained. Is it clear? So, this completes the back annotation. So, what we will do is next is we will go back to that Xilinx command summary, that is what we have seen using wave signals. We have seen the back annotated files, and so what we have done, I have forgotten 2 other aspects earlier, that is we have been handling constraints. I mentioned that we can take the constraints straight away from a file and open one .ucf file, and so we will have a little more insight into these constraints, because this is an important thing that we may have to handle quite frequently if you want to make better timing closures. That is, if you want to speed up operation, you may have to have all this you should know, otherwise you can't try to get a better speed of operation. So, I will just go through this. So, first is we will change the constraints for there are basically 2 constraints, one is clock, other is IO pins. Actually, we are dealing with FPGA design. So, we are going to have a peep into how the your design has been mapped into the FPGA, that we will be seeing, and before that we will see what a clock constraint is, how to give this. I will just read out this. To change constraints such as clock speed and pins, click on tools constraints editor. This is naturally in Xilinx place and route we have to do this, and a window opens, click on global to view clock, and for change of clock from 100 megahertz to 50 megahertz. So, we have programmed it earlier for 100 megahertz. So, naturally half time is 5 nanosecond, 10 nanosecond will be the time period. So, half time is 5 nanosecond. In clock, if you remember in UCF file, that is what we have given 5 nanosecond, because it is as a result of which we had 100 megahertz, and actually this has been taken through the simplify tool, synthesis tool, therein we specify 100 megahertz. So, automatically that has been taken into account, and we change this parameter here to 50 megahertz. That means 5 will have to be changed to 10 or any other thing you can change and see whether it gets reflected. Then replace 5 in period column to 10 and enter. For change of pin, that is for change of clock, and in the same window you have one more option called ports. For change of pin, clock on ports click on ports, and in location column corresponding to the desired signal in the design. I mean all the signals in your design will also be listed, and identify the design particular signal that you want, and then click on that the location, and double click on the selected location column. Another window opens. Enter the new pin assignment followed by OK. Save the constraints file. You may view the .ucf file to see the new changes take effect. After this, .ucf file would have been rewritten with the new constraints that you had taken. And after that, we have one more what is called floor plan. You can actually see where your circuit is residing. So, you can have in terms of the primitive cells we have seen earlier, that also we have a look, and before that let us have a look at the constraints first. So, we have this is the constraints window, and before opening this I will this is the Xilinx window already open, and you remember we had seen this earlier, and it is this version that we are version 3 revision 1. It came straight away from the synthesis, it is a simplify synthesis, and now what we need to do is we go for tools, and then in this you have what is called constraint editor. So, when you click on that, it opens here, and if you click on this, you have ports here, and you have another thing called global here, and it is here you have to mention what it is listing is the actual clock here, and this is 15 nanosecond high it says, and I had changed in between, that is why it was like that. Now I will change back to, and actually this 15 nanosecond is reported here, and if I change I will remove that 1, and it is 5 here, just enter. That is what we have written there on that command summary, and immediately this 5 nanoseconds has taken effect here, 5 nanoseconds here, and so next thing is that is how you change the frequency. You do not have to worry about any other thing. Nanosecond high 50%, it is a 50% duty cycle, it goes from 0 to high, and that is what the clock is for, and clock is listed here, and all other files also, I mean signals will also be listed, provided you get from that UCF file once again, which is not done here, right. And now I will show another UCF file after with all those pins we have mapped earlier, that is somewhere here. You can see the final UCF file will look like this, and you have the place and route itself has mapped it onto a particular pin, all your signals, design signals, and clock is here, and then clock period we have seen is 5 nanoseconds here, and you can even edit a file, UCF file, you can create your own file, and on similar lines, and you can straight away run it right at the beginning. You could have given that .ucf file at that point of time, then it would have taken all the pins etc. With your mapping, your choice will get affected. So, otherwise you can come from this constraints what we have just now seen, and from there also you can change the pins as we have already seen, and I think we did not see the pins here change, and that was constraints global ports, sorry. So, in ports here there is a pin here, say for example this signal let us say clock or B here. So, I can key in straight away there, or I can just double click here, another window opens, you can just key in there. I say 239 here and say OK, that gets reflected here. So, whatever is entered here also appears here in the list. So, when now next step is to save this here. If you save, it will go into UCF file. The warning that it is giving is after you have mind you have made a major change here, which is totally different from what it was earlier. All pin configuration, your then clock, everything you must have changed. So, all this will have to take effect totally. So, in order to do this, you have to go back to the prior to back annotation, straight away to the implementation, place and route, Xilinx place and route implementation. Start from the implementation, then do the back annotation once again, and then make sure the functionality is okay with the pins, and that is how you have to go. So, that is a time consuming thing, and it is precisely the same that we have already followed. Therefore, that particular aspect will not be shown, and it is enough if just see a UCF file. With that, I think you will be in a position to remap your IOs and as well as the clock. We will first see the this UCF file we have already seen here. So, pin 52 for data out to signal and so on it goes. This has been created automatically during place and route, and as I mentioned earlier, during place and route you can see the report browser and get various reports such as pad report or log report. All pad report will contain precisely this, and here also you can have a look. And so, next what we will do is I will go back to this command here, and what we have here is floor planner. Click on tools, floor planner, to open the floor plan or layout of the design. So, this is the design which you can see as a layout, and use help to change the placement, and this is involved. We will not go into depths of this, and because it is quite involved, and right at the beginning stage you do not really require, only towards the end of the project you actually require, and help will take you step by step for that. So, we will see only very essential things of the floor planner, how it looks, without going into too much details. And one important note is, if you change any of the constraints of the floor plan, you will have to run the place and route as well as the back annotation again. That is what I mentioned here. So, you have to run the place and route once again, implementation onwards, then go to back annotation, and only then your new constraints such as pin or clock will take effect. And we will now see the, so what it says here is, you have under tools you have a floor planner here, just click on this. Another window opens called Xilinx floor planner, and here you can see different windows open, and once again you may find it difficult to read. And so, you have what is called placement. So, actually these are all the pins of the FPGA, and your design has been mapped. This is only sequential circuit. You see wherever there is a patch of light here, only those things are your actual circuits here, here and so on. So, in this particular thing, I think it is a 100,000 gate count device we have selected, of which your design is almost a negligible area it occupies. And another point is, there is one more here, and this is what is called editable floor plan, and in this you can zoom if you want here by using this plus. You can zoom further and further. Let us zoom further and see whether we can read something. You can see actual pins here, P220 and so on, 217 and so on. So, these are all the pins here, and one more thing is, you suppose you click on this symbol, a gate symbol here. So, what we have here is, in the editable floor plan that we have seen that this is the layout of your chosen FPGA, say 100,000 gates equivalent, and you can see all the pins marked here on all these sides, and for example pin 3 here, 4, 5 and so on. It is numbered like this, increasing order in anti-clockwise direction, and each of you can see, I wonder whether you can see some faint lines here. They are all basically squares, and in each square there will be a group of primitive cells, for example MUX, LUTs and all the primitive cells which we have already seen, and that will be there. And now what we have here on the left is all your design signals are shown here, and you can, a group of signals you can just click here. For example, I clicked here, and once I click here, I can place that particular part of your design anywhere you want here. So, for example, it's I can place it here. So, you can see here that this particular thing is placed here, and let us, and like this you may have to go and pick different elements, and here we do not have much choice here. So, I have just shown one here, and if you click back on the same thing again, this highlights, in fact it flashes here. If you want, you can remove, suppose you made a mistake, you can remove that and then place it here once again like this. There appears to be some bug, I think you will have to experiment with it, and this is how you in fact it should come freely here, and we will have to investigate why it does not work properly. Anyway, you experiment, I will leave it as an exercise to you, and the main emphasis here is suppose you are not happy with the frequency of operation that you have already achieved, and in spite of synthesis, and you can have extra mileage here by placing this your different parts of the design at any other strategic point, probably very close to the pins, and you can also renumber the pins, and all this will be an added advantage by redoing the floor plan. And once you do the floor plan, so next is to you have to using that pin constraints that we have already seen, we have to renumber the pins, because now with the change this might have been somewhere else here, and that would have come here, and but the pin connections are still the old connections. So, unless you renumber these pins, it will not have an effect over this. So, the step is to locate all this physically, and there may be in a big design there will be a very large number, that will be a tedious thing, and there are if you look into the help, so it will list on different topics, and you can find out how they can be handled for a particular there is an index here, you can go for various, or that is all online documentation as well, and you can use one of the index here and find out so how to place placement something like that. Then you can say display, you can find out. So, you can it has help facility for the placing as placement as well. So, you go through that, you will get it, and there might be bugs which you may have to get in touch with Xilinx to set it right. And in this fashion you can reorder this placement, and then redo the pins by changing the constraints file, and then once again run starting from the Xilinx implementation, place and route onwards, then go on to the back annotation, and that would complete the entire cycle. After you do all this, you are likely to get extra speeding up of a system. That is the primary goal here in changing the pin constraints, and also changing the floor plan. And another advantage is as I mentioned earlier, there are two teams working on hardware as well as software. One team will be freezing on the hardware design right at the inception, along with your Verilog coding in parallel and concurrently. So, that would be possible in this FPGA platform, because you can always come to the fag end of this, that what we are now in, and change all the pin to suit their hardware engineers design. To suit that particular pin assignments, you can redo this pin constraints, you can change, and this would complete all the tools we have seen so far. Model sim for simulation, and then followed by synthesis for using simplified tool, and then followed by place and route using Xilinx, and also to back annotate, and finally the backconnected file we took into the model sim, simulated once again and made sure that the whole thing is intact, and we have also seen how to change the pin constraints, clock constraints, and this completes in a sense all the tools, and we will consider other applications shortly. The application we are going to deal with is PCI arbitration. So, what PCI is, this is called expansion for this is peripheral component interconnect. So, this is a high speed bus, data bus, and if you open your Pentium, you will see some 3 slots available on PCI bus, and this is a typical scenario that we can conceive of in the application that is given here, and the purpose of doing this one is not to go into the details of the actual applications as such, but only to deal with explanation of an ASM chart and how to use an ASM chart in your design, and then to code in Verilog and to implement only the arbitration logic. It is basically an arbitrator controller, and let us consider an interesting example. So, this is for the video application. So, right now what we have is a camera here, and that is basically a video coming in PAL, or it can be NTSC sequence, and this is hardware to grab this video. It may even be a JPEG input, and another input can be a VCR or VCP, and there can also be another format such as XGA or SVGA format straight away entering as a video, and no matter what the video is, this video grabber collects this information. This is going to come in a continuous stream, and this may be even an analog signal which will be converted as a digital signal and finally input here, and what we are dealing with is are the basically in the digital realms, and this is the video in for this. You can think these modules as a simple single card residing on the PCI bus in your Pentium. So, in fact there are other cards here, and this in fact this you are already familiar with the Pentium. So, this is the host what we are calling CPU, and it will have an associated main memory, and in order to connect this host there will be a bridge between this internal bus and the PCI bus, and that is what is called north bridge. Similarly, there will be south bridge etc., and connecting to CDs and other devices, and that is not shown on this, because primary intention is not to go into the design of all this, but only to show you how to design this arbitration logic, which may be residing either in the motherboard of the Pentium, or it can be in one of the PCI cards. In fact, you can view each of these as a card, and this is the video grabber card which is available from third party, and so also a serial parallel to serial interface called FireWire, and this is governed by IEEE 1394 standards. There are 1394, then 1394A, then 1394B standards, and this is called FireWire, and the primary role is to convert parallel information into serial information and send it out here. And out comes the it can be a JPEG stream or a MPEG stream. Once again, in MPEG you have MPEG 1, MPEG 2, and MPEG 4 and MPEG 7. So, no matter what the application is, so the whatever logic you have in order to accomplish this, such as compression, so that will have to ultimately reside in one of the boards, and that such board is what we call video codec, and this video codec, codec stands for coder, that is encoder as well as a decoder. So, it has actually basically two sets of circuitries, and this will be finally residing in FPGA or ASIC, and this is the one which you are concerned about as a designer. Suppose you want to do MPEG 1 or MPEG 2, let us say we do the hardware core, write Verilog source code and go through all the exercises we have already covered, right up to back annotation of Xilinx and use the Xilinx, and finally program a device which will ultimately program the FPGA which is residing in this card. And if it is ASIC design instead of FPGA, naturally you need to house that ASIC which you have designed, and ultimately the actual IC will have to be populated on a board here. And this board also has, like other boards, some first in first out memory here, and if it is video grabber, perhaps you need 1 or 2 frame storage, and it should be available in this first in first out. So whatever image that comes in is basically a raw data, and raw data is already, it's a very huge data, and hence the need for compression, and that compression can be affected only by the hardware, and for which you will have to write the source code. And after writing all that and going through all the exercises that we have already seen before, and you can finally have a bit stream. That bit stream can be downloaded onto the FPGA on the card. We call it video codec, and the primary role is to process in accordance with MPEG, be it 1 or 2 or whatever, or even a JPEG. It can be for still pictures, you can use that. So here what we are going to do is, we see that these are all independent processors by itself, just like your CPU. In fact, all these things will be as complex as a CPU thing, and they are therefore referred to as masters. In fact, you have a PCI bus, it is something like your national highway, or simply called data highway. So on this highway, unfortunately, you can only have one transaction taking place at a time. So for example, if someone, all these things, cards are basically masters, and you have 4 masters here, and of all these masters, and all of them would like to grab the bus. So you will have to have some arbitration done among this, and in a controlled manner only allow each of these devices to access the bus, because there are common resources such as AGP and finally a monitor. The monitor that you see right here is basically on, if it is on AGP card installed in the computer, then it is through this, that is what is being communicated. Host communicates with the monitor in this fashion, and it is all basically through the PCI bus, and of course there is a bridge here which is nothing but an extension of the PCI bus here. And as far as the video application is concerned, how it works is, first you will get your input image here. It will come frame after frame, and it will be stored in FIFO, and then when there will be a bus arbitration which you will need to design. That is what we are going to consider actually, and as per the bus arbitration, and it will decide when to allow this PCI bus access. For example, this wants to access this video codec. In order to download the one frame it has collected, which is already stored here. So when it gets the chance, and first it will make a request to the PCI arbitrator, which we will see in the next diagram, and then it communicates, and via the PCI bus it sends the one frame information into this, and there is a corresponding FIFO here, and that will be received, and encoder starts working on this particular frame and brings about, applies transform such as DCT. DCT stands for discrete cosine transform, and then quantization, and then followed by VLSI, and finally there is also a motion estimation in MPEG. You can dispense with motion estimation if you want just process as iframes, in which case the circuitry will be much less. Okay, no matter what you have here, so we have basically the compression software here, and if it is encoder, it does the compression, and if it is decoder, that is the other half, it will do the decompression. And for decompression, once again you have to get from outside world. For example, let us say we have a computer here, and we want to connect it to another computer which has precisely all these cards, and there also there may be a parallel to serial interface card which is called the firewire, and this can operate at a quite very high speed up to 3.2 Gbps. It's a very huge thing, and in fact you can network here, you can basically connect 63 nodes here, serial connection, whereas in order to communicate with just one another computer, what all you need is just 2 channels here, one channel to go out for the other computer to receive, and whatever similar information the other computer sends, it will receive through another channel. Just with 2 channels we can use it for communicating between 2, and if you have multiple such computers, you can network them, and in which case this same firewire, the very same hardware will cater to 63 basic serial interfaces, and if you want you can expand right up to 64 kilo bytes. I mean, it's not a bytes, 65 536 such nodes you can connect here. That means to say you can network a number of computers, and you can map the whole thing for video conferencing and a video phone, and apart from receiving motion picture, and that is precisely the application is for. And what CPU does is, in order to configure it from one standard to another, for example JPEG to MPEG, MPEG 1 to MPEG 2 and so on, because all this you can have right on the same computer that we are working on, say the Pentium based computer. So from that for that you need the CPU and associated main memory, and what all you have here, if you want to display it you need a monitor, because any picture that you receive from the serial face from the other computer, so you will have to go through this here and do the inverse of compression. So this is the compressed stream that you will be getting here, that is pumped into this, and decoder will do the inverse operation and get the image which is called reconstructed image, which is precisely the same as the original image the other computer has sent. Same is the case with this here. So you can have a bilateral traffic here. Suppose you can send one motion picture using this here and onto this, and the other computer can receive, and in, concurrently you can the other computer can send some other picture, and in parallel you can process, and what you have processed is a compressed stream that you get here. This can be decompressed by this hardware here, which is our which is in our realms for the design, and the decompressed image you can through the PCI bus you can download through, it's not downloading, straight away display it on the monitor through an advanced graphics port here, and I hope this clarifies the total application, and out of which what we are going to consider is only bus arbitration here. So this is abbreviated video grabber, video compressor, codec, then firewire, CPU. There are 4 masters basically, and they have 4 request signals given to the PCI arbiter, which is your current design, which we are going to see, and this it will depending upon the priority, naturally it calls for the highest priority because this is the video image coming here, and video sequence cannot be missed, not even a single sequence frame can be missed. So you had to give top priority to this. Then next high priority will have to be given to VC, that is a codec here, because it brings about compression as well as decompression, and it's all time consuming affair. So and after that compressed image will be sent over this, and this will naturally have a lower priority, and the lowest priority is for the host here, and the bus grant is once again issued by the PCI arbiter as grant here. There are 4 requests and corresponding 4 bus grant here.